All right, welcome to IA 221. This is the introductory PowerPoint, Sensors Overview. And the purpose of this recording is to give you a first pass of all the major terms, the major terminology in the sensors world, and to sort of open your mind up a little bit. You don't expect necessarily to know all the details in this pass, but it's the introductory pass, because once we get into the content of this course, it will give you a lot more detail. And in my experience, once you start getting used to the terminology, hearing it and seeing it applied and hearing it applied effectively, that terminology starts to work its way into your brain and let you help understand the concepts as we dive further into the course. So don't expect to know everything. Let this material just sort of flow over you and ask me questions as we go. So in the introduction portion of this presentation, we're going to talk about terms. One of the first terms you're going to hear is the word transducer. A transducer is used as a generic term across many industries, but in the sensors and the instrumentation industry, it's always a device that converts energy from one kind of format to another in a simple transformation. For instance, I might have a temperature, and I want to convert that temperature into something that's readable by a small computer. And so I would convert a temperature into a small voltage, say between 0 and 10 volts, or a tiny microvoltage in the case of a thermocouple. So a transducer is simply something that converts something from one energy to another. And the output from most transducers is usually some sort of electrical output. It's either an on and off signal for digital outputs, or a signal that varies over a range of voltages or current. For instance, in the example they give you is a loudspeaker. It transmits electrical signal into sound energy. So it's going the other way. It's an output. So a sensor, the definition of a sensor, is a transducer that is used to make some sort of measurement of a physical variable or some sort of physical system. It can respond to a variety of different, what we call physical stimulus, which are, temperature sensors, heat, light, sound, pressure, magnetism, motion. And we are surrounded now by sensors. 20, 30 years ago, you could walk into a house and there would only be a handful of sensors in that house. Now we walk into a house and you are surrounded by sensors, from your Ring doorbell to your devices that let you talk to Amazon, order parts, to your refrigerators, to your TVs, to your game systems, tons of sensors all over your PC. You're surrounded by sensors, and your car is loaded up with sensors, literally 50 plus sensors for some vehicles, all over your vehicle now. So you've got sensors all over the place. Sensors are a particular kind of transducer. So, we here say that sensors differ slightly from transducers in that although changes occur, the changes do not necessarily involve energy conversion. So we're not converting energy, you might just be measuring something, measuring a property. An example they give you is light. Photocell measures how much light there is available. And the example is, of course, for photocell, a photocell will produce more light the more light there is. So the first kind of sensor that we're going to get into are called limit switches, which are just like any switch. They're like your light switch. They're like the switches that you have in any kind of switch all over your dashboard. But they're specially built and very carefully designed to measure when a motion of something has reached a certain point. They're usually specially designed for rugged characteristics. They're usually designed for certain environmental characteristics, and there's thousands of them out there. But all of them have one thing in common. When some sort of physical object causes the little device, whatever it is, there's a whole bunch of different kind of devices, push button, roller, whisker switch, lever, something pushes against that limit switch, it either turns on or turns off. That's all of them. So there's literally thousands of different limit switches out there. In the Sensors D2L site, I think I have a link to Eaton's catalog where you can look and order different kind of limit switches. And when we dive into limit switches in the book, I'm going to spend some time showing you how to order limit switches from Grainger and McMaster-Carr. By the way, for Jackie and Tyler, my two favorite websites for ordering parts are McMasterCarr.com and Grainger. McMaster-Carr is an education of itself, not usually the cheapest source for anything, but a great educational experience. And we're going to definitely look up some parts on McMaster-Carr as part of this course. And Grainger is a great source to find parts as well.
We use both of those at my work.
Yep, they are good sources. I like McMaster-Carr best because they give you free education. And recently I've added Automation Direct to my favorite websites because they have very cheap industrial components that have proven to be surprisingly rugged for their price. And they also have some good education. So here's a few points about limit switches. Obviously, they're either on or they're off. They're like a switch. They're either on or they're off. You basically have two contacts. You can have them normally closed or you can have them normally open, but they're either on or they're off. When something bumps up against it, it turns on. Here are the symbols for two kinds of limit switches. The top one's a normally closed limit switch, and the bottom one is a normally open limit switch. So you can sometimes have the same normally open and normally closed wiring in the same limit switch. So you can buy it and just wire it up one way or another. We have single and multi-pole switches available. And, well, they have limitations. They are mechanical devices. They will fail. If you bump into it with a fork truck, it will break and fall off. They will fail. They are relatively low mean time between failure, but they still will fail. And they are relatively slow. In other words, sometimes that switching action takes that whisker or that lever a good deal amount of time to make the switch. So they're good for low speed applications. Typically, limit switches are used in applications where you've got the movement of some large object across a range of positions. If any of you guys do 3D printing, you know that we often build limit switches into our 3D printers to tell the printer where that 0 position is. So they're used in a lot of different places. The advantage is, number one, there's a million different designs out there that are very robust. If you buy a good high quality limit switch, it's going to last you years and years. It's very capable of handling current much higher than micro switches, than other kind of sensors. So you can actually use them in systems that use 110 volts or 240 volts or some cases 600 volts. They're extremely reliable. Engineers are old like me like them because we're used to them and they're reliable. There's something to be said about that. And it's hard to break them with EMI. It's like that old Ford truck. It's so old that it would run even if we had a nuclear holocaust. All the other vehicles out there lost their little computer chips. Well, a limit switch doesn't have a computer chip either. It's going to keep running no matter what you do to it until you smash it with that fork truck. All right, so now we're going to another class of switches. Now, what's unique about a limit switch is it's either on or off. You can wire it normally closed or normally open, but it's either on or off. There's no other choices. The same thing for these switches. These are called proximity switches. A limit switch, you actually need to touch it. You got to touch it to turn it on or off. A proximity switch, you don't have to touch it. You just have to be in proximity to it. So that's what this word proximity means. Some people use the term prox. I say that a lot too. If you're in the industry, a prox switch is any switch that lets you be nearby your target without touching your target. So that automatically gives you some advantages if you have something you can be nearby to without touching it. Now you have no moving parts. So your mean time between failure, even though it was good with a robust limit switch, can go much, much longer. Now the only thing that can kill you is EMI or some sort of lightning strike. All right, so your prox switches can go a lot longer. And so let's talk about the different kind of prox switches. There's three basic kinds of prox switches that we're going to talk about. There are more out there, which we're not going to get into, but the three basic ones are inductive, capacitive, and magnetic. Now, let's talk about what these terms mean. An inductor is a coil of wire that I can charge up magnetically and I can discharge magnetically. It is an electronic device. It's a little coil of wire. A capacitor is basically a chunk of material that is not conductive between two plates that are. And then you can charge it up with energy and you can discharge it with energy. And a magnetic, well, you know what a magnet is. Magnetic means you've got magnetic energy. You've generated a magnetic. They all work electronically very similarly. They all use some of the same electronic components. Each one of these is a tiny little computer packed into a sensor. Each one of these needs power and has an output. Sometimes they have multiple outputs. Sometimes they have multiple ways of programming it or turning it on or off with extra wires. But all three of these are, think of them as tiny little computers. You need to give them power and you need to get a signal from them. So why do we have proximity switches? Because it's an advancement over mechanical limit switches. Because it could be non-contact, and the inductive we can use for metallic objects. Induction is this coil, so we're creating a magnetic field. So the only thing that we can sense with a magnetic field are things that will change that field. That's inductive. Inductive, magnetic field, things that change that magnetic field turn my inductor on. Capacitive, anything can change your capacitive field. You can, have a jar of water, you can have a chunk of steel, you can have a bit of wood, you can put your hand on it and turn it on. A capacitive, anything can change a capacitive field. In general, they have a range of about 10 centimeters. So you don't have a long range for any of these sensors. So inductive are your coil. An inductor is a metallic coil, and you charge it up with energy, and something comes into that field, then the inductor senses it. And we're going to talk about how that works in a second here. But a metallic object goes near this coil, it changes its magnetic field, and we can sense that, and we know the little computer inside there says, oh, turn on, I sense something metallic. And they can be AC or DC, they could be a variety of different kinds of outputs, and we're going to get into wiring up an inductive prox in the lab. How does it work? Well, we're not going to dive into the details of that today, But inside that little sensor, there are several electronic components, all working together. Basically, it's got an oscillator that oscillates that inductive coil and creates that sensing field, that magnetic field, which is constantly changing. And what happens is, if something goes into that magnetic field, it tends to dampen that oscillation. You can see at the bottom of the screen there, you've got this reduction in the oscillation. So I've got a little computer in there inside that sensor that says, whoa, my field changed sufficiently that I think I should turn on this sensor, and I can turn it on. Now that's usually adjustable. I can actually adjust for the higher dollar sensors exactly what that point of turning on is. So I can, once I get this installed and wired up, I can precisely tune it for my particular application to make it turn on exactly when it should turn on. But it's an inductive field. It's talking about a magnetic field. It really doesn't have a big range. Only a very, very expensive inductive prox has more than about an inch range. Most of them are less than an inch. In fact, the inexpensive ones are usually a fraction of an inch in range. So the presentation goes through how that works. It oscillates the magnetic field, and then when the change is sensed, then it turns on the output. Now, there's a key thing about these sensors. They are not simple devices. These are tiny little microcomputers in these sensors. They have circuitry in them. Doesn't have a lot of complexity, but it has enough to know when an oscillation field reduces to a certain amount, and then an adjustment so I can set that threshold. So it's got some little bit of brains in there, not like a full microcontroller, but a little bit of brains in there. So this just sort of finishes out what I was saying there. So the applications for this are everywhere. Anytime you want to sense a piece of metal coming into range of the sensor. Used all over machine control, conveyors, counting systems, motion control. I used the inductive proximity sensors in motion control. A capacitive proximity sensor is very similar to the inductive, but instead of sending out a magnetic field that's pulsing, it's actually pulsing a capacitor, and it's seeing how that capacitor responds to that pulse. And that capacitor is perched right at the end of that sensor. So now it can sense anything that's going to get close to that sensor that's going to change what they call its dielectric capacitance. Dielectric is that material in the middle of those two plates. So if you put your hand up against a capacitive sensor, your hand becomes part of that capacitor. And it changes the way that field is oscillated. So it's the same sort of principle as the inductive, but instead of sensing metal, now it can sense anything. Capacitive sensors used to be very expensive, but due to mass production, especially overseas, they're getting cheaper and cheaper and cheaper. In my opinion, the capacitive sensors have sort of taken over the market. And we've got a number of sensors we're going to use in lab and talk about how to wire them up. So here's a few key points. You got two plates. So what happens is, let me just show you the little diagram here. Your plate that is essentially the plate that's hooked to the dielectric comes in close to any sort of material, a target, water, glass, humans, wood, anything, even metal. It will change that capacitance. It'll change the way that capacitor reads the world. And so suddenly your oscillation gets bigger. And when your oscillation gets big enough, the little intelligence inside of your sensor kicks on and says, all right, time to turn the output on. So it's almost the same thing. So whenever I say inductor, these are very important terms. I'm going to repeat them over and over. Think an electrical magnetic coil. It only senses magnetic things. If I say capacitor, then I can sense anything. Now, capacitive sensors have actually grown in their quality and characteristics. So you can tune this capacitive sensor to sense out to quite a large range, like 1 inch or more. So you can have a pretty good range with capacitive sensors. And so the presentation goes through some of the advantages. Obviously, they're lightweight, small objects cannot be detected by mechanical limit switches, but anything can change the capacitance. So they can detect anything, high speed, non-metallic, anything. They're really, really good. And they're getting cheaper. So they're used in a lot of applications, and more than just these three. They're now being used across the board. Now, here's the question. If you're in an application where you might have a person lean up against the sensor, which do you want to choose? Do you want that person to trigger it or not? If you don't want that person to give you a false trigger, then you probably want to use the inductive, unless that guy's wearing a wedding ring, in which case he'll still give it a false trigger, because gold will trigger a sensor. All right, so now we're going to talk about a dumber, less super intelligent sensor, and these are magnetic proximity switches. And they fall into a couple categories. The ones we talk about in this particular presentation are the smarter category of magnetic proximity sensors. Basically, you sense a magnet. You sense a magnet. If a magnet's there, you turn on. Now, there are some sensors out there called reed switches, which are really lightweight switches embedded in a bit of plastic. So when I bring a magnet over near that switch, that magnetic field of that magnet causes the mechanical switch to click closed. And those are used, they're very inexpensive, and those are used all the time as sort of door switches or cover switches. So if you pop a cover open, it'll turn off the machine. If you pop a door open, it'll set off an alarm. This particular kind of magnetic proximity switch is a little bit more expensive and actually somewhat rare. And it follows the same kind of circuit as these inductive and capacitive sensors. It's got its oscillating circuit. It senses a magnet, changes the oscillating circuit, and that turns on a switch. So it's a magnetic proximity sensor. So those are the three most common I'll call them proxies. In the category of sensor, which are also becoming more common, which aren't really proximity sensors, are photoelectric sensors. Photoelectric sensors basically use light energy to see if something's there or not. And they are getting cheaper and cheaper as well. And they are becoming more and more flexible with a lot more features. It used to be that your photo sensor, the only one out there was one like your garage door sensor that would send a beam across a room. And if you crossed through that beam, it would, cause your garage door to go back up or trigger an alarm or something along those natures. But now we've got photoelectric sensors that can do a lot. You have photoelectric sensors that can sense color. They can bounce off a variety of different objects and see whether an object's there or not. So you've got a lot of capability with photoelectric sensors. So it's any time you have a sensor which reacts to a change in light. In general, a lot of them are infrared. They're using the infrared range of magnetic spectrum, and we're going to get into that in the chapter here, to send out the energy and receive the energy. Why are we using infrared? Well, the same reason why you would use it on your TV remote. That way you don't have an accidental trigger from a spectrum of light, which is more common. Photoelectric sensors can go a lot further. than any prox. You can have a target across the room, 300 feet away in some cases, and still detect it if it's there or not with a photoelectric sensor. However, the downside is if you have dirt, you've got fog, you've got, I don't know, they show in the movie, these guys, they spray hairspray to see where your photoelectric sensors are if they're breaking into buildings. I don't think that's real, but it's kind of cool. Yeah, if you have anything that kind of can get into the air, if it's got enough mist to show that beam, it might also be reducing the intensity of the beam and will probably trigger that alarm. But all those sorts of things make the photoelectric sensors less reliable than a prox. But distance-wise, you can't beat them. And there's three basic types. You've got the through beam detection. You've got a retroreflective, we'll call reflex, and you got proximity diffuse. So we're going to go through each one of those. We use LEDs nowadays. Infrared LEDs are cheaper and readily available. We can have more than just a solid beam in the TV shows and the movies. You always see this bright red beam that becomes visible if you use hairspray. And then you can fool it by using mirrors and things like that. Well, not in modern systems. In modern systems, we have pulsing modulation, which makes the beam hard to fool. And once you get it set up in tune, it's hard to reflect it and get an accurate reading. So let's talk about this different, I'm going to skip over some of these slides, just sort of obvious. In general, you've got some key components for all photoelectric sensors. Number one, you have a light source. Now, the light source is usually specially tuned to go with a receiver. You've got a sender and a receiver. And in some cases, they're separate devices. So I might have a sender on one side of the room and a receiver on the other. And the sender shoots a beam of invisible infrared light to the receiver. And the receiver is on when it receives that light and turns off when something passes through and turns it off. And then that receiver is a phototransistor, and it converts that energy using some electronics and an amplifier. So it's called a signal converter, an amplifier to an output signal. So those are your basic components. Sometimes they're split into two separate devices, like the through beam, right? And so here's an example of a through beam where you have the emitter or the sender on one side. An object needs to pass through between them. And if something passes through, it'll either turn it on or turn it off, depending on how you wired it. We are going to be playing around with these sensors in class. The effective beam detection area is simply that narrow column, that tube of light that goes from your source to your detector. The sensors themselves usually have a slightly wider area of sensing or sending that energy. And so what this diagram says is that precise beam gives you a very precise way of determining whether an object's there or not. We'll play around with that in the classroom. I can actually tilt it and make it slightly out of alignment and still get it to work properly. Obviously, the further away they are, the more accurate you need to make the alignment. So the through beam has the best long-range sensing. You can have a sender on one side. It could be 300 feet from the receiver. Highly repeatable. Highly configurable. It is your single best option. Obviously, the downside is you have to wire in two separate objects. And it's more expensive. Now you're buying two separate components. So let's talk about another kind of growing field. This is the reflex or retroreflective. Basically, you've got the sender and the receiver in the same sensor, and it's bouncing off an object. Now, the downside is the object has to be pretty close, but now I can use some more brains in that system to decide what kind of object I want it to bounce off of. So it can be bouncing off a very basic retroreflective device, like a piece of reflector or a clear white panel of some sort. So it's bouncing light off of it. Or I can tune it to bounce off of certain colors and turn on only when certain colors are red. So I have a lot of capability of tuning this particular kind of sensor. But essentially, it's got to bounce off something. And the older, less expensive ones have to bounce off of a reflector. And you can get these reflectors just like you get on your mailbox that bounce light off from any angle. So it doesn't matter if the reflector is precisely oriented to the source and the detector, the sensor itself. It could be at quite an angle and still bounce and give you a good signal. The last type is the proximity diffuse reflective. So the big difference here is it detects a spread of the radiation energy, and it can detect any object you want. Not just reflectors, not just white surfaces. So that's enough with photoelectric. There's a whole bunch of different kinds of photoelectric sensors out there. There's actually vision systems we're going to get into in the lab for the first time. We're going to be learning how to use vision systems in this class. But now we're going to, all these sensors we've talked about before are either on or off. They're designed for switching on or off. They've got little electronics packages or little brains in them that let them switch on or off. Now we're switching up. Now we're talking about a kind of a sensor that gives you a number, which is in a certain range, right? So an ultrasonic sensor is designed to tell you a range. You can set it up to be on off, but ultrasonic sensors traditionally can handle a range. They can tell you how far you are from an object by bouncing sound waves, just like you bounce light waves off that diffuse approach for a proximity sensor. I can bounce sound waves off an object and it rolls back at me, and I can use that ping, that sound wave pulse, to determine how far I am from that object. We use this a lot in industry. We use it for judging tank levels. I put an ultrasonic sensor at the top of the tank, and it bounces its signal off the liquid level in that tank. And depending on how empty that tank is, it gives me more and more distance. And so I can use that data to calculate how much material is in that tank. That's a really typical. I also use ultrasonics in the factory floor. When I'm talking about robots, a lot of them have ultrasonics on it so that they know when they're approaching a person or a vehicle or a wall. Ultrasonics are used all over the place. It's generally an excellent tool for non-contact applications. They have some limits, and they're getting cheaper and cheaper and cheaper as well. It used to be that to get an ultrasonic sensor, I have to spend $1,000, $2,000, $5,000. In fact, I've got some broken ultrasonic sensors in the classroom that came from Hershey that probably cost about $10,000 each, new. Now, right now, they're worth nothing. But new, they were worth an awful lot. But now I could buy a cheap ultrasonic sensor for a couple $100. And it'll give me a really same accurate reading as say 30 years ago would have been $1,000. How does an ultrasensor work? Basically, it's got a sender that pulses out a ultrasonic high frequency sound wave, bounces off a target, and comes back. You got a cone, right, that you send out the sound wave and it bounces back. But the key is it senses anything within the beam angle that you're pointing the sensor at in that cone. That's called the beam angle. But if you get too close to the sensor, it stops being able to measure that effectively. It's so short that it can't do its calculations properly to measure the distance. If you get too far, also, it can't measure it properly. So all of my ultrasonic sensors have very specific ranges they can measure accurately. They bounce out a sound wave, and it comes back within a certain range. The sound wave is converted, that distance, say if it's set up to run between 4 feet and 30 feet, it'll convert that distance. Anything between 4 feet and 30 feet gets converted to an output signal. In some cases, it'll be a voltage output. The example they give you here is a milliamps output, 4 to 20 milliamps. So when it's at 4 feet, it might measure 4 milliamps. If it's at 5 feet, it might measure 4.6 milliamps. When it's at 15 feet, it might be 12.5 milliamps. And when it's at 30 feet, it'll measure 20 milliamps. That's the output signal. It's a range of values. So how would I use that signal? I would use that by sending and wiring up that analog input to a PLC. So those of you who haven't taken my PLC class, you're like, what's an analog input? What's a PLC? Well, you guys will definitely be introduced to PLCs by the end of this class, even if you haven't before. Just curiously, Tyler and Jacqueline, what's your experience with PLCs? Have you done any wiring, programming experience working with them?
What is a PLC?
Good. Got to start somewhere. How about you, Tyler?
Yeah, I've done some stuff with them.
Okay. PLC stands for Programmable Logic Controller. I used to require everybody take the PLC class before they take this class, but I've taken that requirement out of there. I will teach you how to use a PLC. It might take you a little extra time. It is a little microcomputer that's designed to run factories.
Yeah, we have a whole bunch of them where I work. I've just never had to actually get into one and do anything inside of it.
Right. Yeah, I know you guys do. So we've got some of your PLCs in my classroom.
Perfect.
Which we're not going to use for this course, but that's okay. All right. So anytime you have a sensor that's analog sensor, that means its output ranges from a value to a value, like 0 volts to 10 volts or 4 to 20 milliamps. That is an analog sensor. All that previous stuff we were hitting on was a digital sensor, on or off, like a bit, 0 or 1. Analog sensors, we can hook up a voltmeter to it and read that range, or we can hook it up to a PLC and use it in the program. So we have these key terms. Resolution. Resolution is the smallest target movement that the ultrasonic sensor can identify and evaluate. So if I have a target in front of my ultrasonic sensor and I move it 1/4 of an inch, is it sensing? If yes, then I know that my resolution is less than 1/4 of an inch. If my ultrasonic sensor has a resolution of 10 millimeter, that means I need to move a whole centimeter, whole 10 millimeters, before it's going to trigger a change in that reading. So that is your resolution. That's the smallest quantity that sensor can measure if you got a change in your situation. And that's true for any analog sensor. You're going to find that same term used. Repeatability is the ability for the sensor to consistently detect a target at a particular point. If I'm moving up to that point, is it precisely that point? Or if I'm moving back to that point, is it going to measure precisely at that point? That repeatability is probably more important than the resolution. I want to have really good repeatability for any of my sensors. That way I can set them up, expect a certain value when a certain physical condition occurs, and know I'll get that. Repeatability is expressed as a percentage of the sensing range. And in especially ultrasonic sensors, it's affected by your environmental conditions. If you have foam on top of your liquid that you're measuring in your tank, guess what that foam is going to do to your ultrasonic signal? It's going to mess with it. If you have vapors on top of your tank, if you have any number of things that can occur, powder, dust, you could have a tank filled with gravel where the tank has basically a big funnel. As you drain material out of the bottom of your physical tank, it creates a big kind of funnel shaped cavity at the top. That's hard to measure accurately. Where do you measure on that funnel? Right in the top, right in the middle, right on the side? It's tricky. So you can have a lot of environmental conditions that make a sensor difficult. And that brings me to my almost last slide here, which is good targets. You always want to have a good, clear, flat, reflective target for your ultrasonic sensors. If you don't, you're not going to get consistent readings. And we also have the last couple terms that are poor targets and unstable targets. Obviously, you want to have few of these as possible, or otherwise you choose a different kind of a sensor. Now, we're going to be diving into other sensors as well. One of the key analog sensors that's not mentioned in this presentation are thermocouples. So we're going to talk about thermocouples and other kinds of temperature sensors in this course. That's the other huge area that we don't mention in here. The book does a very good job about that. And there's a few other odds and ends sensors as well that we're going to get into. Things like bubblers and other methods of measuring height and pressure and so forth, because we've got a lot of different kind of sensors out there. We might want to measure pressure. We might want to measure flow rate. We might want to measure a whole bunch of things. But this presentation kind of gets you guys started with some of the basic terms, shows you two basic styles, the proximity sensor and the analog ultrasonic sensor. And then on the rest of the course, we're going to dive into these and then a whole bunch more after that. All right, so